Hello and welcome to Ed Talks with Khan Academy. I'm Kristen DeSerbo, the Chief Learning Officer at Khan Academy. And today I'm excited to welcome Dr. Begoña Vila, who is an astrophysicist and the lead systems engineer for two of the instruments on the James Webb Telescope. And she was also the deputy lead for operations during the commissioning of all of the Webb instruments after launch. I'm so excited to have her with us today. Before we get started, I want to remind you that Khan Academy is a nonprofit and we do rely on donations from folks like you to keep doing the work we're doing. And you can go to donate.khanacademy.org to donate and help keep us moving and keep us working towards our mission of a free world-class education for anyone, anywhere. I do want to thank some folks who helped support us during the COVID-19 crisis, including AT&T, General Motors, and Fastly. Next, if you want to listen to this interview on audio, or if you want to listen to other interviews we've done, you can go to Homeroom with Sal, the podcast, available wherever you get your podcasts. And with that, let me welcome Dr. Begoña Vila. Welcome.
Hello, Kristen. So nice to be here. Thank you for having me.
It is our pleasure. So let me start out just by asking you a little bit about your education journey. Were you always interested in space, and how did you start out, and how did you get to where you are?
Well, I grew up in Spain and we lived outside a big city, so the skies were very dark. So I remember when I was little, I was fascinated about the changing on the sky at night, right? The different stars, the constellations, and even during the day, the sun and then the moon phases. At that time, I didn't know there was a career such as astrophysics that I would be able to do. So then I did my studies. I was a good student, and then I started in physics and follow my astrophysics degree and my PhD on that field, and then progress from there, as you mentioned, from being in the university as a researcher to moving to the private sector, working to build some of these satellites and observatories that we are going to launch and do the systems engineering. So that has been my path, top level to get here.
Great. Were there particular teachers or courses that you really enjoyed or were influential for you?
Yes, for sure. I loved all the topics. I think I still do. Obviously, I love physics and math, but I also love history and lots of other things. And in those days in Spain, I was going to a Catholic school, and they were all girls, right? And the teachers were all women. But I do remember my physics teacher. She was not a nun, but she was a woman, and she was attractive, and she was very good at physics. So I think that helped me a little bit to know that being a woman or being a girl, you can combine both things. And then later on, once I started on the higher degrees where it was a mixed class with boys and girls, there was also my physics teacher was really good. And I think that's so important, right? When we have these teachers or these people on our lives that are good at what they do and explain things well and we relate to, I think there's such a good encouragement to keep us going on the path we want to pursue. So definitely I have had good support throughout, which is very lucky. Yeah.
Great. So give us your quick pitch about the James Webb Telescope. What makes it unique?
Yes, for sure. It's the biggest, largest telescope we have launched into space up to now. And I think it's unique in two ways. It's unique on the engineering part and it's unique on the science. On the engineering part, the scientists wanted a telescope that could look back in time to the first galaxies and stars that form in the universe and see how they changed to become the planet, the galaxy where we live. And also they wanted to keep looking for life as we know it in other planets, right? If we talked maybe 50 years ago, we could ask, do you think there are planets around other stars apart from our own? And we could have opinions about it. Now we have had some telescopes out there, Kepler and TESS, that have shown, yes, other stars have planets. We think now maybe every star has planets. So Webb can continue to look for those planets, but it can move things a little bit forward, which is, do those planets have an atmosphere? And if they have an atmosphere, does that atmosphere look like the one from Earth? We still don't know if they have life as we know it, but it's a little bit moving in that direction. So from the science, obviously, these wonderful discoveries. But to achieve all that, we needed a big mirror to collect more light and be able to see so far back in time. And we also needed to look into a particular wavelength. Maybe we'll talk about that later, which is called the infrared. It's not the visible light like our eyes. So infrared is heat. So we needed to be able to cool this telescope. So we needed a big sun shield, like a beach umbrella to keep us cold. And those two, the big mirror and the big sun shield, were great concepts, but they didn't fit in the rocket that we have to use for the launch. So Webb is the first telescope that we had to fold to fit in the rocket and open once we are in a space, deploy it. So that was a big achievement on the engineering side that will open the path for future missions being able to do the same. So I think it's wonderful on both sides, the science and the engineering for this observatory.
I love that balance between the two. So tell us about your role. What do you do?
So I started with the Canadian Space Agency. This observatory is an international collaboration, which is one of the super cool things about it. It has contributions from Europe, from the European Space Agency, contributions from NASA, obviously, and university and companies in the US, and then contributions from the Canadian Space Agency. So I started in Canada working on the two instruments that are the contribution. One of them is a science instrument that we call NIRIS, and the other instrument is the fine guidance sensor. So that sensor is the one that's going to allow that the observatory can point correctly to where it should be in space and then keep the observatory stable. Meaning when we are taking an image or a spectra, like when we take a photo with a camera here on the ground, if you're moving the camera, the picture is going to not look very good. So you have to do the same with something in space. You have to keep the cameras steady. So that instrument doesn't do the science yet, but it keeps the observatory stable. So I started working in Canada. And when we built what we call the flight model, the final model that's going to go into space, and those are going to be delivered to NASA, I moved to work directly for NASA, which was really cool, a great experience for me. And then I could take a little bit of a bigger role. I could be involved on some of the testing of all the instruments, on some of the planning of that testing, and then on the activities needed to commission that observatory once we were on orbit, and to continue now shadowing a little bit how the guider is doing for its operation. So I have been very lucky to be part of this observatory for 16 years. So I'm very excited that we are where we are now.
Yes, yes. You can look back, I'm sure, on how far you've come. So it kind of blows my mind to think about holding this stable in space. When I think about, in my head, you think about things kind of floating around, and how do you make something stable so you can get a clear picture?
Yes, so every observatory that you launch, any satellite will have these star trackers that keep track of where the stars are right in the sky, and that will point it to a certain position. But then you really need to get the accuracy. So what the guided instrument does is it takes an image of that part of the sky and is looking for a particular star that the catalog from the ground tells us to find. Find this star, and once you find it, keep it in this position and keep it there super stable. So what we do is we provide the position of that star very accurately 6 times every second. And there is an algorithm that keeps checking. If we tell you that position has changed a tiny bit, there is a mirror that's going to move to bring the position exactly where it should be. And we do it those 16 times every second. The instruments take images in a longer period of time. They can take 10 seconds to take an image. So we are able to keep that precision so they don't even notice any small movement that we catch. So it's a kind of closed loop operation where I tell you something and you react to what I tell you. And then I tell you what I see then. And it's this process that we have optimized for Webb. And of course, you have to work. If you think about the sky, there are parts of the sky where there is only a few stars, some where there are hundreds of stars, some where the stars are very dim, very faint, some where they are very bright. So we have to have different, take all that into account in the algorithm. So, it works well every time, or as many times as we can make it on the first attempt. So.
Yeah, yeah. So it seems like you're doing kind of a combination of engineering and science. Do you think of yourself in both of those spaces?
Yes, I think I consider myself very lucky because I love astronomy. I love astrophysics. That was my kind of my first love, and that's what I pursue right in my career, where I did my PhD and my research. And I was interested on galaxies. Right, I was looking at these spiral galaxies like our own, where you have arms around a center and the arms are rotating. And at that time, when I was doing my PhD, we already knew, thanks to another astronomer called Vera Rubin, very famous, that if we were looking at the rotation of those arms, they were moving faster than we expected when you were further away. That was the first indication that there is some matter there in the universe that we don't know what it is, this dark matter and this dark energy, right? So I was doing research. I had a postdoctoral position in universities in the United Kingdom. But the problem at that time is difficult a little bit to find a permanent position on a university. You can do these postdoctoral positions for 3 years, and then maybe you move to another university. And then as a family, we moved to Canada. And at that time, it was a more stable option for me to go to the private sector. But I still wanted to be involved in space and in research. So I looked for a company that will work on launching observatories for astronomy into space. And then I believe I have still been able to use my knowledge in astronomy, because you have to work with the scientists that want this instrument to know what they need, and be able to meet those needs. And you also appreciate the science, the reasons why you are doing this observatory, and you get equally excited about what we are going to find out. So I consider myself very lucky that I have the astronomy background, but I also was able to grow in this role as a systems engineer, where you are looking at the big picture and how you can make those scientific goals come to life. So it's and maybe for those in the audience, you can see you can think you want to do something when you are younger. I think anything you learn is so exciting that you learn it, and then but you can change your mind. You can decide, I thought I would love this and I have loved it, but for whatever reason I'm going to try something new. It's never lost. I mean, you have a knowledge with you and an experience that will probably benefit the next thing you are looking for. So I think through life, all of us kind of move and get to where we are meant to be or what we like to do through different paths. So I think that's always very important to keep moving forward.
Yeah, yeah, absolutely. I had someone who told me it's easy to look back and explain the path of how you got to where you are, but sometimes when you're moving forward, it's not always clear where you're going next, but you can keep building on where you are. So, yeah, I,
Yes,
I
that's so
appreciate
true.
that.
And
Absolutely.
sometimes Yeah, and sometimes you're looking for something, right? You're looking for an opportunity, and we all have moments where something doesn't materialize. We thought we would really like to do this, and for whatever reason, we don't get that. And at the time, it's disappointing for sure. But it's these kind of things that we say. If something doesn't happen, if you pursue and continue, you'll find something else. And then, as you say, maybe looking back, you'll go, well, actually, I thought I really wanted that, but maybe this other path is good. So I know we all get discouraged sometimes with different through our life, but I think the important thing is to not despair and say, well, that didn't work. Let me try something else. And in the long run, as you say, looking back, maybe everything was for the better, or even if it didn't
Yeah,
seem like it at
yeah,
the time.
absolutely, absolutely. All right, so let's talk a little bit more about the telescope. You talked about pointing and where it is. How do you decide what to point it at?
Hey, that's a very good question. So, of course, you have to decide what you're going to study, right? The team that took part on building the observatory, they have what they call guaranteed time, right? If you were part of the build, the scientists that were involved will have a little bit of time that when you launch, you have these activities that you want to observe, and you will have the time. But then the rest of the time is for everybody. This is an observatory for the whole world. So anybody can submit a proposal. You have a great idea. You can say, well, I want to look at this part of the sky because I know stars are being formed there, or because I know there are some bending of the light. I know there are very far away galaxies there, or maybe I want to look at this particular planet, or you will have an interest as an astronomer. So you have to put a proposal, what we call a proposal, and you indicate what you would like to observe. And then there is a team of scientists that will gather all those proposals and decide which ones are worthier, for multiple reasons, which ones will give the better science. And of course, any observatory in space is overly subscribed, and Webb is as well. But then those proposals are selected, and then there is another team that coordinate them to observe throughout the year. You don't want to be moving the observatory, today here and then tomorrow I come back the other way. You want to be as efficient as possible. So there is a team dedicated to that will say, we have the proposals approved for this year, and we are going to order them such that we are maximizing the observation time for the year. And that was done for the first year. And just now, the proposal requests is open for year two. So any astronomers can now submit what they would like to observe. And again, there will be a process to select the worthiest. I'm sure they are all going to be very good, but with the time that can be fitted on that year for the observations.
Wow, that is fascinating. So we just were showing some of the images that we see, and they look like art coming back. But
Yeah.
what are some of the things that people are learning from them from the scientific point of view?
Absolutely. I know we were, we had launched, the observatory is 1.5 million miles away, 4 times the distance of the moon. And it took us a month to get there. And we had a complicated process where we had to, what we said before, deployed, and then we have to open those mirrors, then we had to align the mirrors, then we had to turn the instruments, calibrate them. So altogether it was 6 months. But even during that time, to calibrate and align the mirrors, we were taking images, right, to be able to do that. And we could already sense, even without it being fully calibrated, how wonderful the images were. And we were all waiting, even us, with bated breath, for those first images that you are seeing some of them there. You can see here the stellar eclipse, right? So this is one of my favorite images, and I think for
Mine
other
too.
people. So we're looking for places where stars are being formed, right? And those stars, when they form, some of them in this image, some of those stars will be forming, but they haven't acquired enough mass to start shining yet. But some of them are shining. When they start shining, when they start doing the nuclear reaction like our sun does, then they generate a lot of energy that pushes the gas that's around them. You need that gas to form other stars. So that nebula shows those newborn stars pushing the gas away, but that pushing of the gas compresses some of that gas and allows other stars to form. So it's an area of active star formation, and we know some of those stars will have planets forming around them. So lots to be learned about that place where stars are being formed. You saw another image, which was this planetary nebula, this big ring around a star in the center. Is actually two stars. And that's the opposite end. That's a star that's dying, right? When a star dies, it dies in this big explosion, which is a supernova, and it generates these rings that we can see on that Southern Ring Nebula, the one we are seeing now. And you can see there all these shock waves that were formed. And this is very important because we know the first stars that formed in the universe were much bigger than our sun, maybe 100 times more massive. And those stars at the beginning only had hydrogen and helium to that's the elements that were there, a little bit of deuterium. But when they explode on this big supernova, they are able to generate then the extra elements that we need: carbon, oxygen, all the elements of the periodic table. So the next stars that are formed have these extra elements, and this is a process that gets repeated for millions and billions of years and that we know we need because we are made of those elements. So we know, when they say we are made of dust of stars, is totally true. We needed those first stars, and over time to give this richness to the medium that eventually allowed us to be there. So all of that for sure. The star formation, star evolution. You saw that other super cool image, which is the first one that President Biden selected, that is looking back in time to those very old galaxies. In there, we have one of the oldest galaxies to date that has been found by Webb, which was born or generated only a few million years after the Big Bang. So Webb has found for now the oldest galaxy. On that image, we can also see these little arcs, which are kind of what we call lensing. That's a star in a galaxy in the background that whose light gets bended. So there is that information there. And then you saw
Can you
briefly
tell us?
there.
Can you tell us about the
Yes,
time thing? About what time? What time are we seeing here? So you
yes,
talked about this being able to see in the past and what that is. Like that is so
yes,
hard for
yes.
me to
I
get my
know.
head around.
Yeah, we keep saying we can look back in time, right? Which is such a strange thing. So we can look back. There was the Big Bang. The universe was formed. First, it was very hot and nothing could form, but eventually cooled down. And we think about 300 million years after that Big Bang, it was cold enough that the little particles started to be able to clump together, and that eventually led to the formation of these initial galaxies, initial stars, and then evolution started. But how can we see that? Well, those first stars and galaxies shine and emitted light, right? And that light has been traveling for billions of years in a universe that is expanding. The universe is stretching. So the fact that that universe is expanded means that this light, as it travels, its wavelength stretches. So when we say the wavelength stretches, it just means it moves on the spectrum of light that we can see. It moves to another part of the spectrum. It moves to the infrared. So with our eyes, we can see the visible, right? We can see what we see on the universe with our eyes is this visible part. And in there, you won't see these objects because their light has moved. So that's why Webb was designed to move and look on
Oh,
this infrared part. So when you take a picture there, then you are kind of collecting that light that has been traveling all that time and be able to then take pictures of these very early objects. That pictures you take is how those objects were when they emitted that light, which was many billions of years away. So that's how Webb is able to look back in time in a way,
yeah,
taking it
got
after.
it. Yeah, that is crazy. Oh my goodness.
I know. And
So
yeah, go ahead. Mhm.
go no, go ahead. were you going to say?
You show there, I know we have been talking about things very far away, but I think lately you have seen that Webb can also look at our solar system, right? We have seen super cool images of Saturn, of Jupiter. There are some more that are coming out. So Webb can also see, which is very important, can see on our solar system anything that's further away than the Earth. This is also tricky to do because we design a telescope that wanted to look for very faint things. And now you're looking at something that's on our neighborhood. They are our neighbors. So those objects are really bright on our cameras. So we have to use a different technique to be able to look at the solar system, and the guide instrument as well has to do something different. So each of the images looking in our neighborhood versus looking far away requires different systems on the observatory, and that's something that also had to be developed. And you can see now some of those amazing images that are going to help us study where we are, right? This is the solar system closer to us, and we are going to learn a lot again about how we came to be, how a solar system like this is being born. And some of the moons in our solar system, we know they have ice. Some of the moons in Saturn and Jupiter are icy worlds, and we know where there is water. We know life on Earth started on water, so anywhere where we see water is of interest to astrobiologists and others, because it's a clue. I mean, how to again
Right.
understand a little better how we came to be where we are now. So
Yeah. So, do you think we're going to find life someplace
uh,
out there other than Earth?
well, I mean, we are special. I think Earth is special, right? We have seen it's not easy to find a planet, and you can see on our solar system we are the only example. So I do think we are special. But on the other hand, there are billions of stars there, and each of them having planets. So I am optimistic that we will find some signs of life on other planets. Of course, they will be very far away. So we need this young generation that are listening to us. We need to be able to travel further than the solar system. So we need lots of new expertise to take us there. But I do think that there will be somewhere there might be life like we know it in this huge universe that we are part of. Yes.
Yeah. We have a question from YouTube from Meherbao. How are the new things that we get to learn in astronomy helpful for us? Are there things that we're learning that are, helping us in our lives?
Yes, I think uh, two parts on this, right? To be able to go into space, we have to develop lots of technologies that then get used on by us, right? So these developments that we have on computers, on phones, some of the materials that we work with on on the ground now, and some of the technologies like the LASIK that we use for correcting eyes, are things that were developed to be able to put things in a space that were lighter, or that we could communicate better, or that we could download lots of data, etc. So there is always applications that come down to the Earth that we use every day. The GPS, lots of things that we take for granted now came from our desire to explore the space. But also, I believe it's part of, in my opinion, of what we are as humans, right? We want to know, I believe, how to understand our world where we live, but I think we also want to know how we came here, and how we can evolve, and how we can continue to explore our universe. I think we have explored the Earth, we continue to do so, but I don't think we are limited to this Earth only. So I think it's very useful to learn all of these things, and to continue looking forward and advancing our understanding of the universe, like, you know, relativity,
Yeah.
and lots of things like that we wouldn't have known unless we are looking at the universe on this bigger scale, and that we are trying to understand. So I think it's important to keep learning, and yeah, at the big side and on the little side as well, on the small world of quantum
Yeah.
physics, but also the gravity and the universe around. Yeah.
Yeah. We have a couple of questions that are kind of related to climate change and global warming. Are there things we can learn about our own atmosphere or the things that, on Earth from some of the things that we're learning?
Yeah, so of course I'm talking about a telescope that's looking for astronomy, the universe, how are things happening, how the things evolve for our solar system, right? How are things interacting? But there are many other telescopes launched into space that are looking at our atmosphere, the atmosphere of the Earth, and we share some of the research to do those observations. And of course, those are the ones that we use to monitor the ozone layer, the carbon dioxide, and it is very important that we know that this is happening to tell us that we do have to look better after our planet. We have grown technologically very fast since the first satellite that was launched, Sputnik, which I believe was 1957. In a very short amount of time, we have learned a lot, and the industrial revolution as well. From the beginning of this century, we have grown a lot, and our planet, I don't think, is not designed for this kind of growth. So I do think we have to do better to look after the planet where we live, because is the one we have. We don't have other. So I think all of these things are always very important to learn and do better on the planet that we have.
Yeah,
Yeah.
yeah. We are already at the half hour, so let me ask one more question. What is something that you're looking forward to, or that we might look forward to from the telescope to come?
Yeah, so again, we know the big themes, right? The things that we are studying, and we are seeing these amazing images. I think we are all looking for something that we won't understand, right? As the scientists keep analyzing the data and taking data, I think we are looking for this little surprise that maybe will show us something that we don't understand to start with. But then as we learn it, it will show us something new. And I think that has been true of all the big discoveries in astronomy, right from earlier on, where we thought the Earth was the center and everything turned around. And some of those early astronomers were like, I don't think that's quite right, right? I mean, there is some data that I'm taking where I don't think that's true. And to say, okay, the sun, and now we understand how all the planets move. And then again, some astronomers said, I don't know, some of those orbits, we are finding something there that we don't understand, that eventually became, the effect of gravity and the relativity. And I think that always happens. I like to mention, I think maybe, this deep image from Hubble, the deep field, which is a part of the sky that when we were looking at it from the Earth, it looked dark. There was nothing there. And when Hubble was launched, time was allocated to observe it for many days. I think it was about 12 days. To show that if it's a dark part of the sky where nothing is there. And this is a very famous image, is the deep field image from Hubble, where, oh and behold, there are thousands of galaxies there. So we realize that, the universe is not as we think. So I think for Webb, even if great discoveries are going to come, we have found the oldest galaxy to date. We have found the first exoplanet with Webb as well. And there are going to be all these wonderful discoveries, but I think we're all looking for something that we don't quite understand to start with. I think that's how we learn and put our thinking cap on and think of something new to understand it.
I love that. I love that. That is a great place for us to end. Thank you so much for joining us today. I learned new things and look forward to what we're going to learn next.
Thank you. Thank you for having me. And I want to encourage all the young kids, to pursue wherever you like and take it forward. I didn't mention it, but an observatory like this one needs, mechanical engineering, electrical engineering, software engineering, astronomers, optical engineering. So wherever your field, something that you like, just pursue it, and then you'll become part of great things that you might enjoy. So go forward.
Thank you so much. And thanks everyone for joining today. We'll see you next time.